Good morning. Thank you for giving me this opportunity to talk to you about some of the work we're doing at WhatsApp. How many people, does anybody here use WhatsApp? So for those of you who aren't familiar, it's a smartphone, cross-platform smartphone messaging app that uses the data plane. I joined the server team at WhatsApp in 2011, and that was my first experience with Erlang. And kind of my primary focus at the company is on system scalability. That's kind of my background. Of course, it wasn't with Erlang before WhatsApp, but it is now. Just thought I'd start out with an interesting little day in the life at WhatsApp. This was this is a traffic graph from last week with a couple interesting little spikes here we have. Any guesses what was going on here?
Patrick's Day.
What's that?
St. Patrick's Day.
Nope.
Pope.
Pope. Yes, Pope. So this one's Pope here. So you can see a little, you can see one spike here when we have news that we have a Pope, and then there's a second spike when we find out who it is. So yeah, it's one of the interesting things we do at WhatsApp is look at interesting things that go on in the world. Okay, so Pope's important in the world. What's more important? Any guesses? If you saw our talk last year, you'll know that sports fans are important. So this is a football match in Europe. You can see a couple goals there, and people love to talk about it when it goes on. So getting more into the topic of this talk, that also caused, so this is shifted by one day. So this is the soccer game over here. You can see there's a couple little, so this is a number of images, number of pictures being transferred between people. And so actually quite a few pictures around the Pope's news. So I don't know what those pictures were, but people had something to share. So here's an overview of what I'm going to talk about. The multimedia problem, our legacy implementation, the old system that I replaced this year, the architecture of the new system, some challenges and workarounds that occurred while developing and deploying that system, and the results and conclusions of that. So let's start out and talk about the problem. So one of the nice features of one of the features that our users like about our app is the ability to obviously share media. So whether it's pictures, it's video, it's audio. Some of that's recorded on the sender's phone, pictures that are taken, videos that are recorded. Some of it's not. A lot of it's actually not. It's stuff that they get from the internet maybe or through email, and then want to forward it to single recipients or into groups. Our app has the capability of creating, very easily creating groups of people that you want to communicate in. It could be about a specific topic, it could be a specific group, but you can send media into those groups as well. We're a cross-platform app, so one of the challenges with media is supporting all the different platforms. So for instance, Apple being Apple, they have to record things in their formats, which is QuickTime for video, Core Audio for audio, and none of the other platforms can play that. So in order for our users to have the best experience, we want this to be a seamless thing for them. So they can send their media into a group or to another user and not worry about what kind of phone they have, what kind of format they should record in, and we want to take care of that transcoding for them. Finally, this system is store and forward only. We don't do any archiving of any of the messages or media that people send. We're basically just a transit point for the media while it's being sent between the users. So the good problem, and it's a fun problem for me as a scalability person, is just dealing with the growth. So we continue to add users on a pretty good basis. As we add more users, each of the users is actually using the service more. They're becoming more engaged with the app. And as it turns out, on top of that, multimedia is growing as a percentage of the usage per user. So we have these three factors that are sort of multiplying to give us a graph that looks like this for media transfers. So the upper one here is pictures. We've got video down here, and audio is the lower one there. But looks pretty exponential. You'll see there's sort of a normal kind of weekly variation in how much people send. People send the most media on Sundays for whatever reason. But we've got a couple special events here. So this is the end of the year. So we've got Christmas here, which is a pretty good spike. And then New Year's Eve, right at New Year's, we've got a really good spike. This one, I bet you won't guess what this one is. It surprised me. This is actually Valentine's Day. So a lot of pictures on Valentine's Day. OK, so our legacy system had the same basic capabilities, being able to send pictures, send video, send audio, but it had some problems. Scalability wasn't as good as we knew that we would need to deal with the growth in usage. The transcoding support was kind of ad hoc. It was initiated by the clients themselves. So the clients would, when they received a media message, they'd see, oh, it's QuickTime, I can't play that, please give it to me in MP4. Or it's a core audio file, I can't play that, give me an MP3. And the rules on the server side for making those transcodings was kind of ad hoc. And finally, the legacy system was in Erlang. And at WhatsApp, our first experience with Erlang was in conjunction with eJabberD, which was the original version of our front ends. And as we've gotten more experience with Erlang, learning how scalable it is, how reliable it is, how easy it makes our lives, now it's feeling like a bigger and bigger hammer. So now everything's starting to look like nails. So nail here, oh, here's a screw, we'll just hit that harder. Here's a watermelon, here's eggs. We're like Gallagher with Erlang. So the goals of the new system were to improve upon the scalability, give us a path to grow the system as we needed to expand with the user base, keep good reliability, and improve the user experience. So just a few words about what that legacy looked like. It was a Lite web server with PHP. We were running it on dual hex core servers with JPODs, 12 SATA drives in those. Just DNS round robin, simple, like we give the clients a host name, they get an IP address, they upload their media, they send it to the other side downloads it from that. There wasn't any reference counting, so it was simply a matter of passing around the URLs for the media. And so without the reference counting, we do need to clean up the media after it's been downloaded. Now, we don't know when it's downloaded, so in the old system, there's just a time-based media expiration. So after a certain number of days, all the media gets deleted. And then finally, I mentioned before that all the transcoding was initiated by the clients, even though the transcoding itself was done on the server side. All right, so in the new architecture, there were some new features that we wanted to add. So again, this is both to help our scalability and to help the user experience. First one I have there is resumable uploads and downloads. So a lot of our customers may be on pretty flaky mobile networks, or they may be intermittently connected, and it's fairly easy to get small text messages through, but when we want to send pictures, which are typically for us about 64K, or videos, which are multi-megabyte uploads and downloads, getting a constant wireless connection for a long period of time to do those may not be possible for all our users. So their only option was to keep retrying, and it would always start over at the beginning. So we wanted to be able to have resumable downloads so that, say they go out of wireless range, or just for whatever reason their connection's kind of spotty, they can retry those downloads, and it succeeds more of the time. We knew we wanted to add reference counting so we could keep track of what was and wasn't used. We wanted to have deduping of uploads so that if I receive something from somebody, a piece of media, and I want to forward it to somebody else, I don't have to upload it again if we already have a copy of that object that's in transit to somebody else in the system. So we want to be able to dedupe that. We wanted server-controlled transcoding so that we could quickly You know, as phones, as new phones come out, or we find out that there are problems through our customer support team that with playing particular videos or what, we wanted to be able to update those transcoding rules without having to push new clients. So we wanted that all controlled by the server side. And we wanted to be able, and the server-side trimming is for low-end clients which don't have the capability to do video editing on the device itself before it's uploaded. We wanted to give them a simple way to at least upload a portion of the video. I'll talk a little bit more about what this is, but a portion of the video and have us sort of trim it server-side to the right size. Okay, so we wanted to do reference counting, so we know we're going to need a database. We want to know what objects we have, who they're intended for, and the transcode mappings between different instances of the same object that are in different formats. So we, you know, being Erlang advocates now and fans, we go to our first choice on a database, which is Amnesia. This is all going to be persistent data, so we put those in disk copy tables. And again, we're dealing with a scalability problem. So this database is all partitioned. We have different islands and fragments. I have a picture that I'll show you in a sec. We do all our operations async dirty to get sort of the transaction overhead out of the way, again, for scalability purposes. But to sort of allow us to do that without creating lots of referential integrity problems, we collapse all the operations for specific objects into specific processes on specific hosts so that everything gets serialized through a single process for a single object. That way we can not completely eliminate the issues that we'd have with not using transactions, but at least for our purposes do well enough. So here's how we split up the database. We have, generally in our system, we run little islands of Amnesia clusters. So an island is a set of hosts which all share one schema. So rather than having one schema for the whole system, which creates lots of problems, both in terms of just the kind of the complexity, but also makes it really difficult to do schema operations because they take a global lock over the whole thing. And even in our small islands, at peak load, it's very difficult for us to do any sort of schema operations. So we try to keep our islands small. So this database is partitioned 16 ways. So half of the partitions go on one island, half of the partitions go on the other island. And then within those islands, we have pairs of hosts, which each host one partition as a primary and one partition as a secondary. So up on Amnesia Island 1, we've got partition 1 on this host, which is the primary. Partition 2 is over here. But they have, I haven't mentioned it yet, but these tables are fragmented 128 ways. So there's 128 fragments for these tables. So partition 1 is going to be fragments 1, 17, 33, 49, 65, and so on. But it also has 2, 18, 34, 50, and 66. So under normal operations, this host is getting all the operations for keys that map to partition 1, and this host is getting all those for partition 2. If one of these goes down, then the partner takes over, and all those operations happen. So then at that point, one host is handling 2 of the partitions. So we've got these pairs. Each of these islands has 4 pairs for a total of 16 partitions. And doing it this way, the other thing to note is the tables are completely, both of these have both of the tables, but they only have half of the fragments are active in each island. So on this island, only the fragments that map to partitions 1 through 8 are active, and the ones that are in 9 through 16 are inactive. There's no records in them, there's no replication, there's no writing, there's no reading, and the reverse is true down here. So we don't get any replication traffic this way, and by partitioning our fragments per host, we only have pairs of hosts talking to each other with replication traffic. So it greatly reduces the complexity of what's going on. All right. So in the new system, we wanted it integrated with the Erlang messaging cluster, our main cluster. And that allows us to do the upload deduping. So the clients talk to our messaging servers over our proprietary chat protocol, and they initiate the media transfer. They say, I've got a video that I want to send. Here's the hash of the file contents. That's sent to the messaging cluster, which then talks to the multimedia system, looks in the database to see if it already has that object. If it does, then it can tell the client, then the message gets routed back to the client and says, here's the URL that you need to pass on to the recipients, whether it's one or a group, and they're done. So there's no need to upload that media anymore. It's already in transit between some other recipients on some other users on the system, so we don't need to upload that again. In the case that we don't have a copy of that object in flight already, we need to pick a server for that client to upload to. So we do the load balancing based on the server that's picked to do that upload is done inside the messaging servers, rather than DNS round robin, which was what we were using on the old system. This allows us to react, pretty quickly to hosts that go down or become isolated on the network, or are having capacity issues and we manually turn off uploads, things of this nature. So stuff that the DNS propagation delay would create problems for us, now we can affect almost immediately about what's going on. Now, that's not completely the case, because after we give an upload URL to a client, they may go away. They may drop off the network, or somebody may, their battery dies or whatever. So there's definitely a decay after we change upload targets. There's a decay of uploads that continue to go to the original host that we pointed them at. The last thing that happens on the messaging servers is the reference management. So after the upload's complete, then there's a second step where the client says, OK, I'm going to send it to these recipients, and we want to attach references at that point. So that we know that, OK, we have an object. Here are the references that we create for the intended recipients. And then once they've downloaded the media, they acknowledge it, and we can delete those references. And that all happens through the chat protocol to our messaging servers. All right. The legacy system used HTTP upload and download for the media objects themselves, the media files. We wanted to preserve that just to have some commonality with the legacy system. But we also like it because it's kind of a known quantity, uploading and downloading files over HTTP. It has support for things like byte ranges, content types, the things that we'd need to implement anyway if we were to do a different protocol. There are some drawbacks, of course. There's an SSL, so we do this over HTTPS, so there's an SSL negotiation each time there's an upload or download. On some of our clients, that can be kind of slow, so it adds a little latency, but that's just what it is. And surprisingly, support for doing bulk uploads and downloads is kind of iffy on some of the client platforms. Now, you'd think, smartphones, internet connected, they'd have really awesome HTTP support. Not necessarily the case for writing applications on some of these platforms, so we've had to do some of our own custom code to do that well. All right, so we needed a web server since we're using HTTP. After a little bit of analysis, but not super great amount of time spent doing this, we selected Yaws. Firstly, because it's mature and had the feature set that we kind of needed. It's a nice balance of support for serving media files, so just being a file server, just a basic static web server, but also had the ability to hook in where we needed to. So creating application modules where we want to be able to look at what kind of transcodings we're going to do, things of that nature. So there's a nice mix there where we can do our programmability. We can insert the application modules, but that doesn't mean that we can't take advantage of all the built-in support that's going to transfer the files themselves. We only really needed a handful of patches for our environment. and we run it embedded alongside in one Erlang node alongside our other server procs that are implementing the service. So for object storage, we do a simple file per object model, basically. This was the same thing we did on the legacy system. We run on FreeBSD, so it's just a UFS2 file system, nothing fancy. We do JPGs, which are directly attached to the motherboard. We try to get as much hardware and drivers out of the way as possible. So one difference between the legacy system and the new system was we knew that images were a lot more popular in terms of object rate, I guess, as opposed to packet rate, object rate, than video and audio. You saw from that traffic graph that I showed you that images are far more popular. So we decided to have heterogeneous storage for those two different things. So we'll put images on fast storage. We'll put the big stuff, audio and video, which isn't as popular, onto slower spinning disks. So our image servers have 6 SSDs, which are now getting big enough. It's practical for us to be able to use that in this case. Now, we don't actually need the full throughput that SSDs can give us in this application, but we need more than the SATA drives can give us. So, so we're kind of stuck in the middle at this point. So we have a little more I/O performance with the SSDs than we really need. We would like to trade off some of that for some space, but it is what it is. We just use a hash directory tree structure based on the file IDs of those objects. There's fewer than 1,000 files in the leaf directories. We use a 16K block size in the FreeBSD file system. This is the same technique we use for our transient message store. So when I send a text message to another user or to a group, that gets stored in their, if they're not currently connected to our messaging servers, that gets stored in our transient message store, our offline store, until they come online, then they can retrieve it. So we have lots of experience with using this kind of storage. So each of the mailboxes is a file on that message store. And so we get about 4 billion cycles a day on those particular servers. And so we know, we have a lot of experience with these, and it's very predictable. We don't have to worry about sort of long-term maintenance of, is this table getting fragmented? Do we need to optimize this index? It's all very straightforward file system stuff, which has been there forever and ever, and it just works great for us. Okay, so after a file gets uploaded, first thing we need to do is identify what it is. So we have a gross notion of what it is. It's an image, it's a media, it's a video, it's an audio, because the client told us that. But we want to know, is it QuickTime? Is it 3GP? Is it MP4? Is it PNG? Is it JPEG? Is it, and so on. So we go through sort of a triage process using Erlang image. Because images are so popular, that rate is too high for us to really be running external code every time we want to identify an image. So this library works well, being able to identify most of the common image types. If it turns out that it's either there's something about the image that that Erlang image doesn't understand. Like for instance, I think there's certain JPEGs where it can't give me the geometry correctly. In that case, we fall back to our external code. So in some cases, if it's an image, we'll run media info and extract. It gets more, it has less error rate in terms of identifying what the media is. And then for the audio and video, we go out to ffprobe, and that's really good at identifying all the parameters that we need to know. So for transcode, and ffprobe, if you're not familiar, is just the sort of read-only version of ffmpeg, which is what we use for the transcoding. So in these three cases, media info, ffprobe, and ffmpeg, we're forking out of the Erlang emulator to go run that C code. And it's basically an OS command call, but I actually went back and basically ripped that code out of OTP and modified it so that it didn't actually launch a shell, put a shell in between, because it was causing some problems for some of the things we were doing. Okay, next thing we need to be able to do is proxy misdirected requests. So I haven't mentioned it yet, but so we put images on fast storage, we put the audio and video on slow storage, but sometimes the images hang around for a long time because they, say, go to a group and maybe some members of the group aren't very active. So we have to hang on to that image until it gets downloaded. So it's sitting there taking space on a fast drive when we don't really need it there. So there's an archive capability that moves stuff from fast storage to slow storage, which means that now it's on a different host. So when we do download, when we send the message, we actually hand out specific host names. So we say, connect to this. This is the host that this media is on, so download it from there. Now, if the objects get moved because they got archived, or for other reasons got moved off of that host, then we need a way to go get it. So on the back end, we reverse proxy to the actual host that the content is on and use Yaz ref proxy for that, which works really great, except that it was a little bit challenging to set the arguments correctly so that the right query args and headers got forwarded with the back-end requests so that the target server that had the content on it could make the right decisions about, it could make the same decisions that the original server would make in terms of what object that it would serve to that client. But otherwise, it works really great. There are a few maintenance processes that run on this system. There's a Reaper process. This is all in Erlang. There's a Reaper process that goes through the database and finds all the references that have been acknowledged, so the media's been downloaded, and references that are really old. So we still have a time-based expiration on media because we can't hold on to everything forever because we do have a small number of people that leave our app and don't come back. So we don't want to hang on to media forever because it's just prohibitive storage-wise. So Reaper drops the references to things that have been acknowledged and they're old, and then we have a reclaimer that goes through and looks for all the objects that don't have any more references and deletes them. Now there's a little bit of built-in delay on that reclaimer so that, for instance, if I send you an image and then you decide to forward it to a colleague or a group, that we hang on to that for a short period of time in case you do that so that you don't have to upload it again. So that's a sort of a configurable delay, but it's on the order of a couple hours usually, depending on how much space we have at the time. I mentioned that the archiving capability, so basically move images that haven't been referenced in a long time from the fast storage, the fast expensive storage to the slower cheaper storage. And then finally a cleaning process which goes through and removes stranded files, and most of the strands come from aborted uploads. So somebody says they're going to send something, they try a couple times, they finally give up because they just really have a crappy network and can't get it to us or something like that. So the hardware specs that we run on the new system are a little bit better. So and this is so basically in our architecture we try to keep everything as common as possible. So most of our boxes are like this. They're these dual octa-core 2690s. So we have 32 logical CPUs. We pack them with RAM. The image servers, which double as the database servers, have 256 gig. The audio video servers have 128 gig. We give them so much. So obviously we need the image servers need this for the database. The AV servers, we give it just for file system caching. So a fair amount of our media goes through the system really quickly. So it's sent from me to you, you download it immediately, and in that case, it's often going to be found in the file system cache. So it just reduces the I/O load on our spinning disks, which are obviously limited in what they can do. On our image servers, we've got the fast storage. So we've got 6 800 gig SSDs on those hosts. And that's for both the image storage and for the database storage. And then we've got 4 terabyte SATA drives on the audio video hosts. Both of these servers, all of these servers are all dual link aggregated GigE front side and back side. So we have 2 networks. We have a front side which talks to the client devices, and then a back end which is where we run Erlang distribution, where we do the media proxying and anything else that we need to do sort of intra-cluster. So here's a diagram of how this all lays out. So we've got our client up here. We've got our messaging cluster over here. So this is our chat-D process. The client talks to that over our proprietary chat protocol. And that's where I mentioned that sort of the media uploads are initiated for the upload deduping and the load balancing. And then finally, after the upload is complete, then the message is sent via the chat protocol because it's a message. It just happens to have media attached to it. We use Erlang distribution in the rest of the system. So the messaging servers talk to the multimedia servers over Erlang distribution. They talk amongst themselves over Erlang distribution. Within each, and then we use HTTPS upload and download directly to the media servers from the client. Now, within the media servers, we've got, as I mentioned, we've got heterogeneous hardware here slightly because of the disk difference. So the images in the database are running on SSDs. The audio and video are running on spinning drives. The database is only on the image side. But basically, we have sort of MMD is our Erlang multimedia server and all the auxiliary processes that run. Our web servers, YAWS. Stud is doing our SSL termination. I'll talk more about that in a minute. We've got the Amnesia database. On the audio video servers, we have another clone of everything except the database itself. And I have one more arrow here. We're doing archiving here from the fast storage to the slow storage. And then this is all sort of horizontally scalable in both directions as we need to grow. So challenges or workarounds with this. One was SSL, and this project was actually being done at the same time as a different project, which was also HTTPS-based. And we discovered that there was, with the built-in SSL, with Erlang's SSL, which I believe, if I'm not mistaken, the crypto stuff is all C, basically NIFs wrapped around OpenSSL to do the crypto stuff. The SSL stuff, however, is all implemented in Erlang, and we found that there was a connection bottleneck for setting up SSL connections, so which we identified by basically the throughput, the number of connections we could connect per second was much less than the raw RSA rate of the machine. So typically, your SSL connection rate is limited by how many RSA private key operations you can do per second on that whatever your hardware is. So our hardware can do somewhere on the order of 3,000 a second for 1K private key RSAs, but we were only getting like 700 or 800 SSL connections per second. So prior to WhatsApp, I was actually at Yahoo, and one of the techniques we did, so we ran into bottlenecks with built-in SSL as well. In our case, it was with Apache, and we discovered that we could actually improve performance by terminating the SSL outside of the web server, and then basically using loopback connections between the external, the thing that was doing the termination. Looked at a couple different options. I had experience with S-Tunnel, but there was a newer one called Stud, which looked very promising, had a good sort of scalability model where you can run as many different Stud processes as you want, and each of those is going to handle as many connections as they want. So it was good for us to be able to scale it out across our many core boxes. So we patched YAWS to be able to accept an HA proxy style header, so one of the problems with terminating SSL outside of the web server is now the web server doesn't know what doesn't have the connection parameters of the end client, doesn't know what the IP or the port is. So we want to be able to have that just for logging purposes, if for no other reason. So we needed a way to pass that from from Stud to YAWS. So it was a pretty simple patch to YAWS to be able to do that. We found with this that the request rate was now just limited by the RSA rate. So so we can do connections at close to the raw RSA rate of the box, which is good. One thing we did run into sort of as the system was scaling up, though, was that with the multimedia stuff, some of these connections are very long-lived because clients may have connections that are pretty slow. So if they're downloading something large, they may be connected for a long time trying to download that. And so we'd get, even though at any given time there aren't that many connections, there aren't that many requests being executed, the download, the long tail of the download could be on the order of over 100 or maybe 200,000 ports being used. Well, on loopback, if we're just using one loopback address, we've only got 64K TCP ports, well, or somewhat fewer than that because some are reserved. So in order to deal with that, we just have multiple loopback addresses. So we have a 127.0.0.1, 0.0.2, 0.0.3, and stud just round robins between these. So basically, we can get as much scalability as we need in terms of concurrent connections. Our next challenge was with sendfile. So I don't know how many of you are familiar with sendfile, but it's basically if I want to serve files from, say, disk to a socket, disk to the network. The simple way to do that is I read from the file, I write to the socket. I read from the file, I write to the socket. Well, if you want to optimize that and let the kernel, instead of bringing all that data into whatever your user process is and then writing it back out, so now it's coming up, it's coming into a kernel buffer, then it's coming into user space, then it's going from user space back into the kernel buffer and back out to the network drive. Sendfile allows you to basically bypass having to bring that stuff into user space. Well, it doesn't work so well, at least it didn't for us on FreeBSD with trying to use async threads. So we want to be able to do as many of these IOs as possible in concurrent manner. So we know we need to have async IO going on because we can't have the Erlang schedulers blocked on slow spinning disks or even blocked on fast non-spinning disks. So what we were seeing when we tried to use sendfile with async threads is that Beam would just stall for a long time. So you get a whole bunch of transfers and then it would stop. And then it would go a whole bunch of transfers and stop. And so throughput was really poorly affected. And this was the case with both file sendfile, which is the OTP version, I think, which started in R14 or 15, and also with the YAWS driver itself. So I simply disabled sendfile in YAWS, and now everything's getting copied through, is doing sort of the naive read from file, write to socket, read from file, write to socket. But now we can run 1,000 async procs, and to be honest, modern machines have plenty of memory bandwidth. We're not constrained by how many bytes we can copy from place to place in the memory, at least with what we're doing. Maybe different with nuclear explosion simulations, but not for what we're doing. Next challenge, amnesia table sizes. So as the system scales up, we get, even though this is a store and forward system, there's still a fair amount of stuff that's in flight at any given time. So per host, we got up to, in the last month or so, we've gotten up to about 1 billion objects per host. So there's 250 million, or 1 billion database entries per host. So there's 250 million objects and 750 million references to those objects. There's a limit to how much RAM we can stuff in a host. And we want to keep this in RAM because we're trying to serve this as quickly as possible. So we moved from so to reduce our memory consumption on the databases, we moved from a sort of naive, here's my tuples, here's my record with nice records, nested records and tuples and strings and binaries and whatever to a highly optimized pack format. So we took as many record fields as we could that could be enumerated, whether it was the geometry of an image or it's the encoding type or all these things that could be sort of expressed as packed fields in an integer, pack those all into 60-bit integers, 60-bit integer being the biggest integer that you can store in a single Erlang emulator word without having to do extra boxing on top of it. So, in some cases that means we've got 3 of these integers and we do some bit string manipulations to get the stuff in and out, but it saves us a lot of space. In some cases, we had keys which were a tuple of ID1 and ID2, and there's actually quite a bit of overhead to doing that as opposed to just having a concatenation of the 2 binaries in a single binary. So we did that. As I mentioned, we hashed the file content to generate unique IDs that we can use to do deduping on the uploads. So originally, each of the hashes, so the IDs were originally derived as a one-way hash of the file hash. And so we'd have to store the file hash to know what it was. by simply using symmetric encryption of the file hash to generate the IDs, now we can do a two-way operation and we don't have to store the file hashes anymore. So that saves space too. Ultimately, we were able to shrink the storage down about 45%, so almost in half. And so this is what it kind of looks like now. We've actually just done a database split. So we got to the point where we couldn't fit any more in a single box. Well, we had to double the size of the database cluster. As I showed you in that slide earlier, it's all sort of power of twos based off of the fragmenting. So we had to double it because it was just getting too hard operationally to keep it just, it was running just at sort of the limits of how much RAM we have. So this is pre-split, but we've got over 1 billion entries in Amnesia on this host, and then we had 8 of those hosts. So there's just a whole lot of records going on at any one time. But it's been working really well for us. Okay, so here's sort of an example of kind of learning little interesting things about Erlang and its associated stuff in OTP. So the reference table is an ordered set keyed by the ID and the reference. The reference is just another big random number. So we need to know, does this object have any references? So the naive way to do that would be, okay, get me all the refs out of the table for that ID, and then see if the length of that list is 0. Yeah, it worked really well until a few weeks, I'd say maybe 6 weeks in, discover that sometimes you get a video which is so awesome that it gets forwarded 1 million times in a day. So now this goes and gets a list that's 1 million entries long, and all you really care about is whether it's 0 or whether it's empty or not. So just there's these little optimization cases just come up all the time. So in this case, this could be translated into basically doing an amnesia next with the ID. Since it's an ordered set, the next thing after the ID is an ID with that is a reference for that ID, unless that ID doesn't have any references, in which case it'll be another ID or something like that. So this this thing basically does one query on does one lookup into amnesia, which is ultimately going to do an ETS lookup and can tell you quickly whether or not there are any references to it. So this is a similar thing, just sort of managing database growth when the system was launched, doing those cleanup, those maintenance processes. The lists that would come back from selects on the database weren't that big. But then they started getting into the millions at a time, and passing around a list of the millions doesn't work great. After, the first cut was, okay, well, we'll do the select and then stick it in an ETS table and iterate through the ETS table. So now we don't have to pass the lists around. Well, even that doesn't scale very well because now the select itself just takes forever. Selects with continuations work much better. I can get me 1,000 things at a time. We're not that concerned that it's a snapshot in point in time. We're not using transactions anyway, so we're not worried about isolation of this select. But this gives us a lot more scalability on doing those types of things. We've had to do a bunch of DB migrations, like for instance, when we did the packing of the objects. We've got a completely different record format. So now we gotta sort of change the engines of the plane while it's flying. So we do that basically by doing a lazy migration. So we'd have both tables active, and any reads would read from the new table. If it's not found there, read from the old table. When you go to write it back or write a new one, you write it to the new table and you delete it from the old table, and then deletes would delete from both tables. So this would just allow us to sort of, as the system's running, gradually migrate things from the old system to the new system, or the old table to the new table. Since the new table's smaller, we know we're not going to run out of space because things are only going to get smaller the more it goes. Again, we're not doing any transactions, but everything that's operating on a single ID is going to a single process. So it's all serialized, so we don't have to worry too much about referential integrity problems. And then finally, when enough of the conversion has happened lazily, then we go through and do a final select, get all what's left in the old table, and do migrates on those. Okay, bandwidth was a big thing to deal with. Turns out our users are super hungry to share media, awesome videos and pictures, and a single host would easily fill up its 2 gig of uplink bandwidth without even breaking a sweat. So we've sort of been dealing with a soaring bandwidth bill, and this is where the server-controlled transcoding is advantageous, because now we can take a look at, well, what are the things that are costing us the most? What are the biggest things? What are the things that are most popular, which, when you multiply it out, cost us the most in terms of bandwidth? So, we've constantly been tweaking the media parameters to cap sort of, so believe it or not, so sometimes, a lot of times we'll get, say, video from an iPhone, which is recorded 1920 by 1080. So full HD on the phone at like 18 megabits a second. Just ridiculous encodings, which is going to be sent to another phone, which is going to go on a screen this big. So we can, by looking at those and saying, okay, this is ridiculous. This 12 meg video does not need to be sent to all these clients. We can opportunistically transcode those down and down convert them to something. A lot of cases, those really big ones will shrink from down to 5% or 2% of their original size. It's just remarkable. Some other things we do is we count the number of times a certain thing gets downloaded and force a down conversion. If it's like I said, if something that's getting forwarded millions of times, sometimes we have to sort of force that to slightly smaller, worse quality, just to deal with that issue. So what are the lingering issues? We don't have any storage redundancy on this. It's, like I said, it's a transient message store. So we're not sort of worried about long-term redundancy, but it is sort of a risk that we need to deal with eventually. There's some memory leakage on the database host. So over time, they grow, their RAM usage grows, and haven't been able to track it down yet. Some sort of fragmentation in the ETS tables or the binaries. I mentioned that schema ops under load are difficult. I mentioned that we're tweaking the transcodings for playback issues that come in from our customer support people or that we notice. Now, so we're trading off squeezing things, our bandwidth against our CPU. So we don't have unlimited CPU that we can use to transcode things. So there's sort of a balancing act that has to be done between how many things we shrink versus how much CPU we have to do it. And then obviously ongoing capacity planning and management. Here's what this memory leakage looks like. So there's basically no growth in the database here, but you can see our RAM utilization is going up until we do a restart, then it starts down here and it goes back up. We do a restart, it starts down here. So this is one of the issues we're still trying to identify. This is what CPU utilization looks like on our audio-video service, which are doing the transcoding. So it sort of follows our daily periodicity in terms of traffic. But you can see we're using all the CPUs. So as I mentioned, we have 32 logical CPUs on these things. So there's 16 cores hyper-threaded. But we can get up over 80% utilization on this system, which is pretty awesome. So what's our peak scalability? So this isn't the capacity. We haven't hit our capacity yet. But over New Year's Eve, we transferred 214 million images that day at a peak rate of about 8,800 images per second, which is a lot of pictures per second. The thing that was blowing us away was how much bandwidth we could push out of just a small number of boxes. So 29 gigabits was our peak output bandwidth on that day. So this is what that holiday week looks like. So here's Christmas here. Kind of a peak here. It's more of a day-long peak for images. You notice that video down here is more popular on Christmas than it is on New Year's, but the reverse is true for New Year's, for images. Images are more popular on New Year's than on Christmas. You can also see that there's a couple different time zones hitting in terms of where New Year's Eve is hitting, but you can see it's a pretty good spike above what our normal peaks were. So we need a fair amount of headroom on this system to deal with that. So ultimately, it turned out Erlang is just fine for pushing lots of bytes, but it's not necessarily good at everything. So I mentioned doing the SSL termination, we moved that outside. Certainly didn't want to deal with doing like the media identification or the transcoding of all the different video and audio formats when there's a great tool, FFmpeg, that at our disposal. So we just found that it was much easier to integrate Erlang with the existing tools to do that. Another thing that this turned out to be great for was for the transcode configs themselves. So a lot of these tweaks require code, not just kind of, so it'd be hard to create a sort of a configuration language for, you know, this maps to this. It's really nice to express it in Erlang code and allows us to deploy the changes quickly. We don't have to reload a config file. We just push the code out, load the code, and now the configs are live. And this raises the value of doing the server-initiated transcodes because we can do it on the fly while the system's running. So here's an example. Here are a couple sample configs. So this one, so we're doing a pattern match here. For Android devices that are getting video, they can support as a container type MP4 and 3GP. They can support video codecs, H.264, MPEG-4, and H.263. This is the cap on the geometry that we want, 720 by 480. We give them a maximum bit rate. They can support AAC and AMR codecs. So we pattern match this for Android, so we can tweak this for all Android devices. If we wanted to drill down even more, we have the device type itself. Like we want to do a GS4, we can do this, so we can be even more specific. On iPhone, here's an example of that. On iPhone, it supports MP4 and QuickTime, but not 3GP. It supports 264 and MPEG-4. In the default case, we're going to do 480 by 360 at 15 frames a second, which is what I think the 3 can do, the iPhone 3. But then if it's an iPhone 5 or 4S or a 4, then we can do 1280 by 720 at 30 frames a second. So we can tweak these things per device. We can handle this all on the server side. We can roll these things on the fly, and it just really makes it nice. Here's an example of what top looks like. You probably can't read it because it's kind of small. Of what top looks like on one of these systems. So we run the Erlang schedulers unbound, so because we're running all these other things on the processors at the same time. So we've got Beam up here that's using 120%. So again, because this is a multi-core machine, it doesn't add up to 100. It adds up to much more than 100. So 120 up here. These are each of the stud procs. So we run 16 of the stud procs, and they're each using about 4 to 5% of the CPU for doing the SSL termination. And then we've got a bunch of these FFmpegs, which are running down here doing transcoding. They're niced so that they don't get in the way of serving. So a single transcode doesn't get in the way of serving everybody else's media. But you can see they use a lot of CPU. So this guy's running, we run the FFmpeg single-threaded, so that it doesn't swamp the box. But so this one's using, they're using about 45% each of a CPU, not since there's 16 CPUs, that's plenty. Done. Any questions? Yeah.
I have a two-part question. Sorry, this is something that's being fair for what you said, but I was wondering what's the representation in the database of the transcoded objects, or you are not keeping track of that and you're only doing it on demand on the fly?
No, we keep track. So basically, so the question was, what's the database representation of one of these transcode links? So there's a transcode table which is keyed by object ID, and then it's a bag, so it has multiple entries. Each entry has the media parameters of the transcoded version and ID of that version. So for instance, so let's say we send a QuickTime. Somebody records a video on their iPhone. It comes in QuickTime. We send that to an Android device. Android can't play QuickTime. That download default thing would say, oh, well, you can support MP4 and 3GP. MP4 comes first, so we're going to prefer that. So then it would look in the transcode table and try to match, are there any existing transcodes that meet those parameters? Do they have, does it meet the container type? Does it meet the codec type? Does it fit within the specified screen geometry? Does it have the right bit rate? And so it can just scan through that list, and if it finds a match, then it has the ID, and it can serve that object instead. And then when we do a transcode, we always update that table with the entry. As it turns out, there aren't, videos, well, I don't actually have the figures. I think videos, there aren't as many transcode links as I would expect. But it's about even split between transcodes that we do on the demand and ones that are served that have already been done. So I think it's about 15% get transcoded on the fly because we don't have a matching transcode, and about 15% are reused because we already have a transcode that matches.
There's a couple of questions that I have. Is there any kind of heuristic optimizations that you are using for the use cases of a group chat instead of a regular one-to-one chat?
Optimizations for a group chat versus a one-on-one chat. Well, only to the extent that because, I mean, this was actually true of the old system as well, but the same object gets sent to everybody. The difference now is because each person in that group has a reference, we don't have to keep that object forever. So as soon as we know that everybody in the group that it was intended for has acknowledged that they downloaded that media, then we can remove it. But we don't do any specific sort of, we're going to pick a transcoding that most of the people can do. We sort of do that on a global scale. So when we first started out, a lot of the transcodes were very specific to the device it was going to. But now they're a little more generic so that we can reuse as many transcodes as we can so that we're not spending a lot of CPU on transcode. And we've as I mentioned, we've capped some of the media parameters. Originally, we would serve as good a quality as we possibly could. So it could be the original, which was a 12 megabyte full HD video, but that just becomes cost prohibitive, especially if that gets forwarded. So we've capped that. And besides, not only does it save our bandwidth bill, but it saves the user's bandwidth bill too. So it's kind of a win-win when we make those determinations that, well, let's shrink this to something that looks good, but it's not outrageous. Yeah, back there.
Can you come back to the slide where you showed us the holidays stats? Yeah. So can you clarify what those peaks are? Because do they represent only the usage in the US or worldwide?
No, this is worldwide.
Right, but doesn't mean that it's because at the end.
Why is this one so tall? I'm sorry, say that again?
There's a pattern there in
yeah.
All of those pipes.
Yeah.
Not that one tall, the average, right?
Okay.
Those ones in the middle.
Yeah, these?
So what I'm assuming is that if there is an even usage all across the world, then you would have some sort of even graph, right? But
well, I mean, so the question is why do we have this daily variation? One reason is because our users, we have a lot more penetration in Europe, which is one reason, and we also have the Pacific Ocean here, where there's not a lot of people.
So what I would assume is that those pipes come from Europe usage?
So they start out in Asia. So this is like Asia, India, Europe, and some of the others. It turns out that different media are more popular in different places. So pictures are super popular in Europe, videos popular in other places, and so this graph doesn't necessarily reflect what our messaging traffic looks like. It happens to be what the picture traffic looks like. Right. And also when we get out of Europe, Europe's in mostly in 2 time zones, whereas once you get to North America, or once you get to the Americas, now you've got 6 or 7, I guess, that stuff gets spread out over. They're in the East Coast.
East Coast?
Yeah.
Right. Would it be more convenient to distribute the servers so you can handle better load in other continents?
So the question is would it make sense to distribute these other places? Turns out not really. I mean, our hosting provider is basically the same for us wherever we're. Because this isn't super latency sensitive, we're not doing real-time voice or video. These are bulk uploads and downloads. So the latency to where between the user and the the servers doesn't really affect the user experience. It's just easier for us to keep it in the US for now.
Right. And another question, there was a rumor, I don't know if it's been confirmed yet, of adding games to WhatsApp in order to be able, well, there is this line competitor,
Mm-hmm.
which was launched with gaming services already. So I'm wondering if that's for real, if that's going to be Erlang powered.
I don't think we haven't said anything about.
Oh, it's just a rumor.
Yeah, that's just a rumor.
Right. Okay. And also the last one is, where do you think the physical limits for your platform are?
The physical limits in terms of what?
If you keep escalating in terms of users.
Well, for most of our systems we feel are pretty horizontally scalable. So you know, so we don't think that we don't know of limits like we're really worried that once we get to this many users or this much usage that we're going to have to re-architect something. You know, this system was there's this system and there's our address book system, the one that helps you that helps keep your contacts straight. Those were sort of the last two that were built on a legacy platform and weren't as scalable as we'd like. Now everything's sort of more horizontally scalable on the Erlang platform, and so we feel pretty comfortable with it. Sure.
So you said you were using distributed Erlang for your back-end communication.
Mm-hmm.
Are you experiencing any of the chattiness problems that people have with distributed Erlang in terms of like when you horizontally scale that, you know, the nodes?
No. So the question is, have we experienced any problems? And I won't be upset if you guys leave. I know we're over time now, and like it's lunchtime. Have we experienced any problems with chattiness on the Erlang distribution? And the answer is pretty much no. Most of our so we architect the system so that it's not a many-to-many communications thing. So you know, we have specialized classes of servers. It's all one Erlang cluster, but we have like little mini clusters of specialized functional servers, and they talk to other groups of things. So the only thing that really goes all to all is the distribution heartbeats, which to this point haven't caused us a problem. We've had more problems just with the sheer volume of even just one-to-one. Some of our biggest problems are actually the amnesia replication between a pair of hosts. Because on some of our hosts, the update rates, you know, the event rates are so high that, that we get these little, we were overrunning the switch ports on the back-end network. So we went through a period of sort of growing pains, kind of like in the fall last year, where we were working with the hosting provider to tweak their switch configs, and this is where we started going to dual links on everything to double the buffer space. We made some tweaks on our side. So our biggest problem has been, on the distribution side, has really been overrunning the network gear because the boxes are just able to pump out packets so fast onto the network that we overwhelm the switch gear.
That's awesome.
Yeah.
Yeah, so I'm just curious to find some pretty like subtle bottlenecks. I'm wondering about what you use for profiling and metrics to help find them.
Well, I don't know if you saw my talk from last year. I talked some about the tooling that we used in that, if you haven't had a chance to look at that. For this, it's a lot of actually just kind of watching the system. I mean, the one thing that most of our systems use kind of as we're planning capacity while the system's running is a utility I wrote in Perl. So when I first got the WhatsApp, it's like, okay, I got to learn this Erlang thing. So I spent a couple weeks like, you know, reading the book and looking at the syntax and stuff, and like, okay, I'm not getting anything done. So I went to Perl, wrote this utility to basically monitor system statistics like network packet rate and bandwidth, disk IOPS, virtual memory, like I think, like these guys are generated out of those systems. So for the MMS stuff, and actually for most of our stuff, when I'm not doing hardcore, like let's find out where the next bottleneck and beam is, it's more about looking at these types of graphs and trying to figure out, especially when we have glitches, like we'll have some sort of glitch go on in the system. We can go back at those logs of the system stats and say, okay, here's what happened. It looks like we had, looks like packet loss on the back end went through the roof, and so these things stop being able to talk to each other, and that's when we go back to the network operations guys and like, are you seeing anything on your switch graphs, and so on. Yeah.
When do you generate the refs? So when you publish a message, I guess, in the app, does the publisher wait until it gets a ref, until transcoding happens, or does transcoding happen at some later point in time?
Transcoding happens when it's downloaded.
Okay.
Yeah. The only case where it happens not in response to a download is that are those cases where we're tracking how many times something's been downloaded, and once it reaches a threshold, like, okay, we've already spent, we've already sent 20 megabits on this thing, so now we're going to try to downconvert it, because it's basically, okay, here's a threshold for when we'll look at objects, and we'll look at the object and say, okay, it's bigger than our minimal size. So if something is smaller than the maximum size that the recipient is configured to accept, but it's bigger than our minimal size, then we'll just send it through as long as it doesn't need to be transcoded. But once we've sent that object enough that it looks like, okay, this is maybe one of those things that's going to get forwarded a lot, then in the background we'll initiate a transcode to shrink it down to that minimal size, and then from then on, people that come in will get that minimal size using that transcode lookup table.
So when I publish, let's say, an image or something, the ref gets generated, and then that message ends up, it gets sent to all of the recipients that I'm sending the message to. Then like transcoding happens on the receipt side, right?
Right.
Which is basically on demand, like
right.
Recipients connect and
yep.
the media gets transcoded and some file gets persisted on disk
right.
somewhere, which then gets served up by you.
Right, exactly. Yeah, and you can see this. You can see that delay. Sometimes when you download a video, like if if for instance you record a video on iPhone, you send it to Android, you can see the delay. You can see the transcode delay because you'll say download, and it'll wait. There won't be any progress on the progress bar while it's doing the transcode, and then it'll start downloading. So you can see that delay.
Have you experimented with like sorry, just one more question.
Yeah, sure.
Have you experimented with like a front-end web server to like add caching so you don't hit yaws and like the BPM?
Well, so the question is, have we tried to front end it with something that would cache? Frankly, if I was going to front end it, I'd probably use the same stuff. I mean, as I said, sort of in the results, I think that this is pushing bytes as fast as we can. We could add more RAM onto those AV boxes and cut down the I/O load on the spinning disks. Our image servers are constrained by RAM for the database and size of the SSDs. And we just keep pushing for bigger and bigger SSDs as they become available. On the audio video servers, we're constrained by seek capacity on the spinning disks and transcode CPU. And so we try to balance it so that we run out of everything at the same time. Like we run out of RAM, we run out of CPU, we run out of disk seeks all at the same time. And that's what we know we need to add more machines. But so far, it feels like we can push as much as we need to out of these boxes. In fact, going in after Christmas, we went back to our hosting provider and said, we pushed this much output. What happens if we push 4x that on New? Because we weren't sure what the difference between Christmas and New Year's would be. And they were like, oh yeah, we got you covered. And because I think, like I said, those audio video boxes can easily push 2 gig each. So we have an uplink capability of, I don't know, 100 gig or something like that, but which is a lot for just a small number of machines. Anything else? Yeah.
You mentioned that somehow you map those audio video
Yes. Well, okay, so the question is what happens if the server that's hosting a particular object fails? And it goes back to one of the lingering issues I said where we don't have storage redundancy now. So if a server becomes unavailable, so let's say it crashes and it's in the process of rebooting, at that point, users will just have to retry the download. So their downloads will fail. They need to retry those. When the server comes back, those downloads will succeed. If we actually lose a drive, then we lose that media, which like I said, is not optimal. We've had pretty good experience. We haven't lost too much media so far. Like I said, it's not an archiving service. It's a transient message store. In most of these cases, that media is still on either the sender's phone or maybe somebody else it was sent to. So it's not like we're losing something that people are expecting us to store for them. It just happens that that particular transfer is going to be lost because we lost that drive. But it's something that we need to address. Anything else? Yeah, sure.
Have you had any operational issues with Amnesia yet? We used to get lots of problems with network partitions causing Amnesia to go into that mode where it needs manual recovery.
Right. So the question is, any problems with Amnesia, operational problems with Amnesia, especially around network partitions? We've been pretty lucky. Our backend network is pretty reliable. And so but that's part of the reason that we keep our islands small. So even though our cluster's big, the number of hosts that are sharing one Amnesia schema is small, so the chances are much smaller that there's going to be a partition within an island. But it does occasionally happen, and for most of our cases, it's just a matter of we kill one of the nodes. We figure out, we decide which of the nodes needs to be killed. We kill it, we start it, it replicates, it loads everything from the peer, and we're up again. So in practice, it's a well-known sort of recovery strategy, and our backend network is reliable enough, and we keep our island small enough that it hasn't really caused us too much pain so far.
But when the schedulers are blocked, you can get that problem even if it's not actual physical network issues. Because the heartbeat comes
sure,
and then
yeah,
nodes think it's dead, but it doesn't think it's dead.
Right. So cases of node down when the network's not down, it's just the pings failed. That doesn't happen very often for us. And off the top of my head, I can't say all the things that we may have done to tweak our environment. So we have done some tweaking of sort of distribution in terms of buffer sizes. I think we changed the default tick time, but I can't tell you what we changed it to. And we don't get a lot of cases like that. I mean, usually when we get a node down, it's because the node went down. Either its network went away, or it blew up out of RAM, or something like that. It crashed for some reason. There are very few cases where we get a node down where it was just kind of in a funky state where it was up but not up, or not up as far as distribution thought. Okay, I'll let you guys go to lunch. Thank you.